three sections here tonight. And so the first one is going to be from 2.4. So we're going to be looking at finding the zeros of polynomials. Okay. And so sometimes we can have these really big polynomials, and we want to be able to narrow down what the zeros potentially could be, right? So how can we do that? And so that little blurb up at the top of the page, that really goes into the whole theory behind that. I'm going to break it down for you a little more simple, I think, and say, basically, if you look at that very bottom sentence there, it's saying if we take the factors of the last term in our polynomial and divide that by the factors of our leading coefficient, any combination of those will be possible zeros for our polynomial. Okay, so let's just look at that in action. Okay, so again, we'll look at this right here. So we're saying we want to look at all the factors of our constant term. Well, our constant term here is this negative 15. So we want to look at all the factors of negative 15. And we want to divide that by all of the factors of our leading term. Okay, the leading coefficient of our term. And so that would then be the factors of 4. Okay, well, let me write the word of with each of these. Factors of negative 15 and the factors of 4. Okay, so essentially, when I'm looking at my factors, right, that could be 1 and 15. 3 and 5, right? So 1 times 15, yes. 3 times 5, yes. However, I could also do negative 1 times negative 15, right? So we're going to do plus or minus of each of these terms. So I'm going to just plus or minus 3, plus or minus 5, and plus or minus 15. So what that's saying is positive 3 times positive 5, or actually, because we want negative 15 here. So positive 3 times negative 5 gives me negative 15. Or negative 3 times positive 5 also will give me negative 15. Okay? So that gives us all of the combinations for our factors of negative 15. So for our factors of 4, that can be plus or minus 1, plus or minus 2, and plus or minus 4, right? So negative 1 times negative 4 is 4. Negative 2 times negative 2 is 4. Positive 2 times positive 2 is 4. Okay? And so that is how we set this up. And now we want to do every combination, right? So each of these over each of these over each of these, right? So how does that break out? So that's saying I can have plus or minus 1 over plus or minus 1. Well, that really is just plus or minus 1. Okay, so our first one will be just plus or minus 1. Then I can have plus or minus 1 over plus or minus 2. So I could have, that would be plus or minus 1 over 2. And then I can have plus or minus 1 over 4, right? So do you see how we're just building out all of these possibilities? So we are, we're putting each one of these with the other, okay? And then we move to the 3. So then we say, okay, that is 3 plus or minus 3 over 1, plus or minus 3 over 2, plus or minus 3 over 4. Okay? And then we carry on and we do the same with the 5. So that is plus or minus 5, plus or minus 5 over 2, plus or minus 5 over 4. And then we move on to the 15, which is plus or minus 15 over 1, plus or minus 15 over 2, and plus or minus 15 over 4. So that gives us all of the possible combinations of zeros. No other value is going to be a 0. These are the only potential ones. That does not mean that every single one of these is a 0. It just means if we're trying to narrow down to find out what the 0 is, these are the only things that we have to test. Okay, question. Let's look at some more examples to help us get a better grasp on this. Okay, so this top example up here, we have our positive 3 and a 2. So in this case, we want to look at our factors of 3 divided by our factors of 2. Okay, so that is plus or minus 1 plus or minus 3 divided by plus or minus 1 plus or minus 2. So there's a lot less factors here than there were in the previous one. So I'm going to write this one just slightly a little bit different because last time you remember I did the 1 and over each of those. This time let's do every numerator over 1 and then every numerator over 2. Either way is fine. I'm just showing you different ways. So this one would be plus or minus 1 over 1. This is plus or minus 3 over 1, plus or minus 1 over 2, and plus or minus 3 over 2. So we have a total of 8 possible different zeros that we could have for this particular problem. Okay. Now, this problem isn't asking us to just list our possible zeros. This one's actually saying, hey, go find the 0 and tell me what that multiplicity is. Okay. So we can do that by using our synthetic division. So let's just pick one. Let's just start with 1. And excuse me, we have 2, 1, -5, -1, and 3. Those are just our values from up here from our problem. So we're going to bring the 2 down, and that gives us 2. 2 times 1 is 2, plus 1 is 3. 3 times 1 is 3, plus -5 is -2. Times 1 is -2. When we add that to -1, that gives us -3. Times 1 gives me -3. That's a 0. Because that ended in 0, that means that x minus 1 is a factor, right? So x minus 1 is a factor, and x equal 1 is a 0. So that's what that's telling. Okay, and that's all because of, remember from last class period, that remainder theorem, we ended with the remainder of 0. Therefore, 1 is a 0 of this polynomial. Okay, question. So, but we want to keep going because we want to get all of our zeros. So we do know that we know that 1 is a factor, but let's keep using 1 and see if it maybe has multiplicity of 2, right? So now we can, I'm going to bring this up here. We can do this again. And we bring this down and we have a 2. 2 times 1 is 2. Add that to 3, we get 5. 5 times 1 is 5. Minus 2 is 3. 3 times 1 is 3, plus -1 is 0. So that means that x minus 1 is a factor, and x equals 1 is a 0 again. Okay, and so And just copy that and put it here. So now that means that x minus 1 is a factor with multiplicity of 2, right? So if we're looking at this problem here, that means that this one, if this was x to the 4, then this is x cubed, x squared, x, and that's constant. If that's x cubed, then this here is x squared, x, and a constant, okay? And so this gives me, I have a factor of x minus 1, and then what's left is what's on this line here, which is 2x squared plus 5x plus 3. Let's go ahead and just copy this and bring that up over here because we could factor this just a little bit further. I didn't mean to cut it, I meant to copy it. So we can factor this piece of the polynomial a little bit further. And so we can factor that so that we have x minus 1, and this becomes 2x plus 3, x plus 1. So by using our synthetic division, we were able to factor that polynomial into all of its zeros, right? So my zeros then here, my zeros would be x equals to 1 with multiplicity of 2, and x equal to, what's going to make this here equal to 0 is if x is equal to negative 3/2. That has multiplicity of 1, and x equal to negative 1. Each of these have multiplicity of 1. Okay, question. Okay. So let's look at our next example. So for this one, same thing. We want to find the zeros and their multiplicities. So the first thing, what I would ask you guys to do is I would like you to take a minute to just do the factoring piece. So what we have in green up here on this previous problem, I'm going to give you guys a minute to do that, and then we'll work through the remainder of the problem together. All right, so who would like to help me with the factors of -5? Anyone?
1 and 5.
1 and 5, right? So we can have plus or minus 1, plus or minus 5, right? And 1 is the only thing is itself, right? So we have plus or minus 1 there. And so that this one actually simplifies quite easily, right? So we can either have plus or minus 1, plus or minus 5. So we can have a positive 1, a -5, a -1, or a positive 5, okay? So when we look at these, we can, let's do our synthetic division. for the sake of this class, so you could do 1, put 1 in there, you'll see it is not a 0. Put -1, you'll see it's not a 0. But for the sake of this class, I'm going to just go to the one that it is, and that is 5, mostly just to save us a little bit of time. So we put in the 5. Now let's say this was the third one that we're testing, right? So we put in 1, -2, -14, -5. Okay, so that is a 1. 1 times 5 is 5. That gives me 3. That is 15, which is a 1. And that is 5. So I get that 0 there, which tells me that x equal to 5 is a 0. So x minus 5 is a factor. And x equal +5 is a 0. Okay? So like we did with the previous one, if this was x cubed, then this is going to be x squared, x, and our constant. Okay? And so that leaves us here with, we have a factor of x minus 5, and we have x squared plus 3x plus 1. This one we can't really factor by traditional terms, so we have to use the quadratic formula. Just as a reminder, the quadratic formula is -b plus or minus the square root of b squared minus 4ac divided by 2a. So when we're looking at this one, that is our a is equal to 1, our b is equal to 3, and our c is equal to 1. So we can plug all of that in here. We get that x is equal to -3 plus or minus 3 squared minus 4 times 1 times 1. All of that divided by 2 times 1. And that will simplify to -3 plus or minus the square root of 5 over 2. Okay, so when we're looking for the zeros and their multiplicity, we would say here that the zeros are x equal to 5, multiplicity 1, and the x equals -3 plus or minus square root of 5 divided by 2 is our other 2 zeros. And those also have a multiplicity of 1. Okay? Question. All right, so a couple of theorems just to put here in the notes for you so you don't have to dig through the textbook, but there's a fundamental theorem of algebra that basically just says that if we have a polynomial of a degree that's greater than or equal to 1 and it has complex coefficients, then the function itself has at least one complex 0. And remember, complex, we often interchangeably use that for imaginary numbers or complex numbers. Okay. We have the second one there. We have our linear factorization theorem. And so that's basically saying that whenever we're doing our factorization here, if n is greater than 1 and our leading coefficient is not equal to 0, then we can, if we end up with something with where it is like x minus c1, c2, etc., then those are going to be complex numbers. The conjugate zero theorem, that is, I mentioned this last class period, I believe, but where they have to come in conjugate pairs. So if I have A plus BI, then I also have to have A minus BI because of the conjugate pair rule. And then the number of zeros of a polynomial. So if the polynomial is, again, of degree 1 or more, then, and it has complex coefficients, then the function has exactly n complex zeros, provided that each zero is counted by its multiplicity. Okay, and so we'll see some of this in action. So the first example we have here is we have, given that 1 minus 5i is a zero of this function, we want to find the remaining factors. Well, we know that if if 1 minus 5i is a zero, remember the conjugate pair, that tells me that 1 plus 5i is also a zero. Okay, because remember they have to come in pairs. So we can do our factorization. We have 1 minus 5i is a zero. It told us, this tells us, right? So our problem is 1 minus 3. I'm going to leave a little more space since we have the complex numbers. 28 and negative 26. Bring this down. So 1 times 1 is 1. 1 times negative 5i is negative 5i. When we add these together, we can't add an imaginary portion to a non-imaginary portion. So we just have 1 minus 3 is negative 2. And then we don't have any imaginary in the other part. So we would just bring that piece down. Okay. Over here on the side, like I did last class, if I have negative, if I have 1 minus 5i, and now I need to multiply that by negative 2 minus 5i. I'm going to do this by the FOIL method. So that is multiplying our first, outer, inner, last. And that's going to give me negative 2 plus 5i plus 25i squared. Remember, I squared is the same as a negative 1. So that is, we'll make this here is negative 1. And so this will give us a total of negative 1 times 25 is negative 25 minus 2. So that's negative 27 plus 5i. So this is going to be negative 27 plus 5i. Okay, so 28 minus 27, that is 1 plus 5i. So now we're going to come over here and we have to do this again. We have 1 plus 5i times 1 minus 5i. And that's going to simplify down to 26 when we do the FOIL. So that would come up here as 26. And when we do the math, that is 0. And you can see that that is a 0, right? So now, based on this, just like we did on the previous ones, we can do our conjugate pair. Remember, our conjugate pair is 1 plus 5i. So now we can do that for this problem. So we bring this down and we have the 1. So this is 1 plus 5i. So now you can see I have a 5i in both terms. So I can do the math on those. So I have 1 minus 2 is going to give me a negative 1. And the positive 5i and a negative 5i, those cancel. So now I have negative 1 times 1 is negative 1. And negative 5 times 5i is a negative 5i. So when I do the math there, those cancel as well. Okay. And so this leaves me, so up here, if this was an x cubed, this one was x squared. So this one here is an x as I'm leading off there. So that gives me here that this term is x minus 1. Okay. And so my zeros are going to be, what's going to make this here 0? If this is a factor, then x equals +1. So if this is a factor, this is a 0. Okay, so my zeros are 1 minus 5i, and 1 plus 5i. Okay, if we wanted, so it wants us to do the zeros and find the remaining, and it wants us to factor it, right? So how do we factor that? So this would be x minus 1 minus 5i. That's one factor. And then we had x minus 1 plus 5i. And we had x minus 1. So simplify this by distributing this negative to each of those terms. And we ultimately end up with x minus 1 plus 5i times x minus 1 minus 5i times x minus 1. Okay? Question.
Professor, I didn't get the part minus 20. How did you get the 20 minus 27 plus 5i? Minus 1.
Minus 1
Well,
here.
1 minus 5. Yeah. No, the minus 27 plus 5i.
This. We
Yes.
did it from this work right here. So you have to, because I have to take this value and multiply it by this one,
Mhm.
right? So that is 1 minus 5i times -2 minus 5i. And I do that by foiling them together, my first, outer, inner, last, right? So 1 times -2 is -2. 1 times -5 is 1 times -5i is -5i, and -5i times -2 is -10i. I mean, is +10i. So a +10 minus a 5 is +5i for that one. And then -5i times -5i, that's +25i squared. And remember, I squared is the same as -i. I mean, is the same as -1. So that makes this right here -25. And my negative sign, I accidentally erased that right there. So -25 minus 2 gives us that -27. And then the 5i just comes down because there was nothing to combine it with.
Oh, got it. Thank you.
Any other questions? Okay. So now let's look at this last example of this kind here. We have the given that x is -1/2, we want to find the remaining solution. So the first thing we could do here is determine what possible zeros there could be. So to do that, we will do factors of -9 over the factors of 2. So that is going to give me ±1, ±3, and ±9. Those are all the factors of 9. And for 2, it's ±1 or ±2. Okay. So I'm not going to list out all the zeros here, but that is, we know all of the combinations that we could put together. This tells us that x negative 1 is a solution. So we can put negative 1/2 over here. And our problem, we have 4, 3, 2, 1, 0. So we can put all of those here. We have 2, negative 1, 17, negative 9, negative 9. Bring that down. 2 times negative 1/2 is negative 1. That gives me a negative 2. Negative 2 times negative 1/2 is 1. 17 plus 1 is 18. 18 times negative 1/2 is negative 9. That gives me a negative 18. Negative 18 times negative 1/2 is a positive 9. And you can see that that gives us a remainder of 0, which we expect, right? Because we know that it is a 0 because the problem told us it was going to be a 0. So now when we want to move on to the next step, we want to pick some combination of something that we know is also a 0. So in this case, I'm going to just do positive 1. Again, we could try various different things. And if it comes up with something that's not a 0, then it's not a 0, and you have to try another one by trial and error. Okay. So I'm going to just pull this up here a little higher. Bring this down, and that is 2. 2 times 1 is 2. That is a 0. So 18 plus 0 is 18. 18 times 1 is 18. That gives me a 0 here. So like before, this was x to the 4, so this was a x to the 3, so this here is x squared. So that means that this portion right here is 2x squared plus 18, because we have 0 x's and 18 constants, right? So if we come up here and we say 2x squared plus 18, set that equal to 0 so that we can find out what the zeros are. We can minus 18 from both sides. So we get 2x squared equals negative 18. Divide both sides by 2. We get x squared equals negative 9. Take the square root of both sides, and you get that x equals, really, when you have this negative, right, this is the same as saying the square root of 9 times the square root of negative 1. Remember, the square root of a negative 1 is an imaginary number. So the square root of 9 is plus or minus 3. And then we have that I out there. Okay. So this problem, then our solutions, right, or our zeros are the negative 1/2 that it gave us, positive 1, and plus or minus 3i. Notice that I have 4 solutions and I had an exponent of 4. Okay. Question. Okay, so if we need to find a polynomial of a lower, of the lowest degree possible, and we're given some zeros, in this case, we're given 3i, but if we're given 3i, we know negative 3i is also a solution, because remember, they come in conjugate pairs. And 2 with the multiplicity of 2, okay? So that means we don't know what our constant is out here, but we know our factors are x minus 3i, x plus 3i, and x minus 2 squared because of that multiplicity, okay? So what we can do here is let's just FOIL these together. and this one is the same, right? It's like saying x minus 2 squared. And so we can multiply all of these out and simplify. So this is going to give us a times x squared plus 9 times x squared minus 4x plus 4. And now we can FOIL this one more time. We have to do it to all three pieces, right? And when we do that, we get that a is x to the 4, a times x to the 4 minus 4x cubed plus 13x squared minus 36x plus 36. And that's as low as we can go. We can't figure out what our A is because we don't have enough information for that. But in the next problem, I'll show you how you can figure that out. Okay? Question. All right, so here we want to find a polynomial of degree 3 that has the following zero. So negative 2i means we also have to have a zero of positive 2i for that conjugate pair. And x equal to 4 is also a 0. Okay, but this time it tells us that when p is equal to 0, our solution is 32. So we can actually solve for a in this problem. Okay, so our polynomial is equal to a times each of these terms. So that's x minus 2i, x plus 2i, and x minus 4. And that's going to simplify to a times x squared plus 4 times x minus 4. So that was really just by combining the first two terms here. So multiplying those gives us x squared plus 4. Now we'll factor all those out and we end up with x equals x cubed minus 4x squared plus 4x minus 16. Okay, so that's where we ended this previous problem, right? We had our function is equal to that. Well, now we know that when p of 0 is equal to 32, right? Because we were given that as part of our problem. And therefore, if we know this, we can plug that in to our equation here and get that 32 is equal to a times 0 cubed minus 4 times 0 squared plus 4 times 0 minus 16. Okay, so that is 32 is equal to negative 16a, and a is equal to negative 2. Okay, so p of x then is equal to negative 2 times x cubed minus 4x squared plus 4x minus 16. Distribute that out and we get negative 2x cubed plus 8x squared minus 8x plus 32. Okay? Question. All right, so this next section, we're going to try and determine how many positive real zeros, how many negative real zeros, and then the difference will equate to how many imaginary zeros. So to do this, we can take the count the number of sign changes within our polynomial. Okay. And then for the positives. And then we'll substitute in negative x for our x and simplify, and then count the number of sign changes, and that's going to be our -0. Okay, so first of all, you see I go from here to here. I'm going from positive to negative, so that's one sign change. Here I'm negative to negative, not a change. But here I go from negative to positive, positive to negative, negative to positive. So I have 1, 2, 3, 4 sign changes. Okay. But in doing this, we have to say you either have 4 and then we decrement by 2 because the conjugate pairs come in 2. So I could either have 4 positives, I could have 2 positives, or I could have 0 positives because the imaginaries have to make up the others. Okay. Now, if I want to calculate my negative, now we're going to do this, but remember we're subbing in negative x. So essentially, when we sub in negative x, everywhere we had an odd exponent, we're really just going to change the sign in front of that. Okay. So this becomes negative x to the 5 minus x to the 4, because it doesn't impact the even one. Minus, so now that's a positive 14x cubed plus 32x squared plus 176x plus 320. Scoot this over a little bit. Okay, so now let's look at our sign changes. Change this color. So we have from negative to positive, and everything else is positive. So we only have one sign change. So we only had one, and we can't decrement that by 2. So these all have to be a 1. Okay. And so if our exponent is 5, our total multiplicity here, this has to always add up to 5. So if I have 4 positive and 1 negative, I'll have 0 imaginary. But if I have 2 positives, 1 negative, then I have to have 2 imaginary. If I have no positives, 1 negative, then I have to have 4 imaginary. Okay, so for the exam, I'll give you something like this, and I'll just ask you the 2 positives and negatives. But just know that they have to add up to this value up here or something less than that if we're adding in imaginaries with it. Okay. And we'll go over another one of these in later on this evening when we do the exam review. Okay. Question. All right, so the last topic for tonight is really just looking at upper and lower bounds. And so essentially, what we can do here is if our C value is greater than 0, and if both the remainder and the coefficients of the quotient are non-negative, then our C value is an upper bound. And then if our C is less than 0 and the coefficient and all of those conditions are met, then our C is going to be a lower bound. Okay. And so this problem here just wants us to show that 4 is an upper bound and -2 is a lower bound. Okay. And we can do that by looking at the signs. So what that is if all the signs are positive, then it's an upper bound. If the signs alternate positive, negative, then it's a lower bound. Okay. So when we're looking at this one, it's telling us 4 and -2. So if I look at 4 first, and we have 4, 3, 2, 1. So we have all of them in order. So we could just do 6, -17, negative 12, 23, and 12. Bring this down. So that's 24. 24 minus 17 is 7. 7 times 4 is 28. Minus 12 is 16. 16 times 4 is 64. Plus 23 is 87. 87 times 4 is 348. That is 360. So what you see here is these are all positive. Therefore, this is an upper bound. So these three, when you put 3 dots like that, that's just saying end of that, such that we have this upper bound. Okay. So when we look at it with the negative 2 and do the same, we have 6, negative 17, negative 12, 23, and 12. Bring that down. That's going to give me a negative 12 minus 17 is negative 29 times negative 2 is 58 minus 12 is 46 times negative 2 is negative 92 minus the 23 is negative 69 times negative 2 is 138. And that gives me 150. So you can see here, I'm alternating my signs. I have negative or positive, negative, positive, negative, positive, negative. Therefore, that tells me I have a lower bound. Okay, question. All right, so we will move on to the next section. This is section 2.5. It's rational functions. So in this section, we're going to apply some of the notable behaviors and such to look at and describe infinite behaviors of a function. So a rational function basically is just saying if I have a polynomial and I divide it by another polynomial, so long as the polynomial in the denominator is not equal to 0, then I have a rational function. Okay. And so what we have here is, let me put the parentheses around that. So in notation form, as I mentioned, I believe last class period, when I see X and then that arrow and C, this little plus sign, I don't know if y'all see that. That plus sign, think about that in terms of the word right. You could also think of it, our positive numbers on our x-axis are to the right of the y-axis, and our negatives are to the left. So that's how I keep the plus and the minus straight in my mind, is when we're talking about plus, its values coming from the right, and if it's minus, its value coming from the left. Okay. And so this terminology, we're going to touch on it in terms of algebra. For those of you who are going on and will be eventually taking calculus, this is a really important concept that you will get on day 1 in calculus when you're starting to talk about limits and such. So we're not going to talk about that here, but you definitely want to have an understanding here to make your life easier if you're moving on to calculus. Okay. So if we want to look at this graph and I want to determine what is the value of my function when my x is going to infinity. So, right, if x is going to infinity, that means that x is coming out here as far as I can come out here. As I go far, far out there, how is my function behaving, right? And so as I get larger and larger, you see my line here gets closer and closer to this value right here, which is equal to 1. So it's coming from above, right? So you can see that our graph is this blue line here is the one that's kind of driving that. And as we get way out there to infinity, right, we're going to just get closer and closer to that y equals 1. Okay? Question. So now if I want to look at it in terms of my my x value is getting closer and closer to negative infinity, then I'm going to be coming on this line, right? As I get closer and closer to negative infinity, as my x value does, then my line gets closer and closer to this y equals 1, but this time it's coming from below. Okay? Question. Now let's see if my x is getting close to 3, right? So we're looking at, here's 3, right? And I want to look at it from the right. So we're approaching 3 from my x is approaching 3 from the right. My y value goes up to infinity, to positive infinity more specifically. Okay. And then as my y value approaches 3 from the left, so now I'm coming here, but I'm getting closer to my y value of 3. My x value of 3, but from the right or from the left, then you can see that this goes down to negative infinity. Okay, question. So I have a little bit more example here. Let me put these parens around. So again, well, let me get a different color because there's red on that graph. Let's do green. So here, as x approaches c from the right, so x approaches c from the right, we're going to go up to infinity is what this is saying, right? So how do we draw that? We would just say as x approaches from the right, it goes up here. Because that red dashed line is an asymptote, we can get really close to the line, but we cannot cross it. Okay? As x approaches c from the left, right? So we could have something that looks like this, right? Because we're coming from the left and we're going up to positive infinity. So both of those, and this one we could have come down from like this, right? We don't know exactly what that shape is. We just know that it's coming from the right and it's going up to infinity. On the second one, we're coming from the left, getting really close to that asymptote line C and going up to infinity as well. For the next one, we are coming from the right? So we're coming from this direction, but as we get closer to that line, our y is going to negative infinity. So it could be something like this. Okay. And similarly, our line from the left is getting close to negative infinity. So it would look something like that fourth one. Okay. Question. Okay. So if we have these two polynomials, we'll say P and Q, and they have no common factors other than 1, then to locate the vertical asymptote of our function, We really just need to determine where the denominator is equal to 0. Okay, that gives us vertical asymptote. Okay, so let's factor our denominator here. This is x minus 5x plus 1. Okay, you can see that there are no factors in the numerator and the denominator that are the same. Okay, so since there are no factors that are the same, we have an asymptote. We have a vertical asymptote when x minus 5 equals 0 or x plus 1 equals 0. Because if either of those two equals 0, our problem is undefined and we cannot have that. So that's why we would have a vertical asymptote there. So that occurs where this is x equal to 5 or x equal to negative 1. Okay? So if x is 5, that function cannot exist. Okay? Because it would be undefined. If that function is negative 1, it is also undefined. Okay? Question. Let's factor the second one. This is x minus 3, x plus 1. Now, notice here we have a term in the numerator and the denominator, right? So what we say here is when you have a term that is in both the numerator and the denominator, that means we have a hole in our graph at x equal to 3. So because if x equal to 3 were to be a solution, then we would be undefined, right? But in this case, because it is a multiple of something that is already in the numerator, we actually don't stop the graph there. We let it kind of go across it and we just put a hole in the graph at that point. So what would that look like? So if we had a graph, and let's say this is 3 right here. And so if it was something coming here, normally we would have that as an asymptote, right? But when it's a hole, we just put a circle here and the graph can continue on. Okay? So that's a hole. Versus on the other graph over here, where we are negative 1. So if this is negative 1, that is an asymptote. And so we actually have an asymptote at x equal to negative 1. So the graph cannot exist at x equal negative 1, but we just put a hole at x equal to 3 because it is a multiple of something in the numerator. Okay? Question. Okay, so for this last one, we have x squared plus 25 can never equal 0 because 1, the 25 is positive, and 2, anytime you square something, it is also positive. So this will never equal 0 because there's no value you can put here for x squared that makes that denominator 0. So in this case, you would have no vertical asymptote. Question. Okay, so let's look at horizontal asymptotes. So again, let me put these here. When we're looking at horizontal asymptotes, that is, we have this line is a horizontal asymptote if it approaches D as x approaches infinity or negative infinity. Okay, so here as x approaches infinity, so we're saying as x gets out here, our function approaches, so it could be something that looks like this, right? D. It could have also been something like this, right? Our x is still approaching infinity, but our function itself is approaching that asymptote at that line D. Okay, so actually I'll put this one on here. So you can see it could have been either way. Okay. For the other graph, as we are approaching negative infinity, right? So my x is approaching negative infinity, or we could be approaching negative infinity from the underneath side. Okay. Question. We have a couple of rules when it comes to our horizontal asymptotes. So really, this is what you kind of want to commit to your memory. Basically, this looks confusing. It's a lot of gibberish, but really at the end of the day, it's just saying if I have some constant value raised to, this would be something like 5x to the 4th, where an is equal to 5 and x is equal to 4. So that's just saying a sub 4 is the 4th constant is the constant a sub 4 and it pairs with the x to that n. Okay, just a notational thing. So basically, we're just looking at this first term here, and we're saying if our n is greater than m, so if our exponent in our numerator is greater than the exponent in our denominator, then we have no horizontal asymptote. Okay. If our n value is less than our denominator value exponent, then the line y equal to 0 is a horizontal asymptote. Okay. And if our exponents in the numerator and denominator are equal, then the line, this should be BM. Okay. Then whatever our constants are right here is what is going to be our line of the asymptote. Okay. So we'll look at some examples of those. All right, so our first example here, let's go ahead and let's factor, or we don't have to factor. We're looking at this. We are looking at our first two terms. So we end up with 3x over x squared. So in this case, my n equals 1 and my m equals 2. So since n is less than m, my asymptote is at y equal to 0. Okay. So I would have an asymptote here at this line y equal to 0. So we'd have this asymptote right here. So you can see this piece of the graph gets close to it. This piece of the graph gets close to it. The one thing with the horizontal asymptote, that can be crossed given certain situations, unlike a vertical asymptote, which may never be crossed. Okay. All right. So let's look then at our second example. Our second example here, we have 3x squared over x squared. You can see that our n is equal to 2 and our m is equal to 2. So they have equal asymptotes. So then our line is y equals 3 over 1 because it's the constant with each of the terms. So that is a 3 divided by 1. So that is at the line y equal to 3. And you can see here that there is that asymptote in here at y equal to 3. Okay. And our last one here, you can see that we have 3x cubed over x squared. So n equals 3, m equals 2. My n is greater than my m. Therefore, I have no horizontal asymptote. Okay, question. Okay, so we have this graph of a rational function. And as I mentioned a while ago, a vertical asymptote cannot cross that line. However, it's possible that sometimes a horizontal asymptote will cross that line. Okay. And to determine if the function has an asymptote that crosses, we can do this. So here we see we have n and m are equal. So that means that y equals 2 over 1, which is 2, is our horizontal asymptote. Okay. So let's set our line equal to that. So we can say 2 equals this 2x squared minus 4 over x squared minus 3x minus 1. Okay. We can multiply both sides by x squared minus 3x minus 1. So it cancels out in our denominator over here. And this is going to give me 2x squared minus 6x minus 2 equals 2x squared minus 4. Okay, let's combine like terms. So minus 2x squared minus 2x squared. Let's add 2 to both sides. So these two terms go away. And we're left with negative 6x is equal to negative 2. Okay. Actually, let me. Negative 2. I wrote this wrong here in the denominator. This is a 4. And so this would have been a 4. And this would be 8. So we're adding 8 to both sides. And so this is a positive 4. So we can divide both sides by negative 6, and we get that x is equal to negative 4/6, which is negative 2/3. Okay. Since it has a solution, then we can say, yes, it crosses at negative 2/3 too. Okay. And on your exam, you probably won't have one where it asks you where does it cross. It'll just be what is your x and what are your horizontal and vertical asymptotes. Okay. We have another kind of asymptote though. That is what we call a slant asymptote. Excuse me. And a slant asymptote occurs when the degree of your numerator is exactly 1 greater than the degree of your denominator. And if you have a slant asymptote, you cannot have a horizontal. And if you have a horizontal asymptote, you cannot have a slant. You can have both slant and vertical. You can have both slant and horizontal. You just cannot have slant and horizontal on the same graph. Okay. All right. So let's look at an example. So when we want to find the equation of a slant asymptote, we really just divide the numerator of the function by the denominator. And the quotient will be that linear slant asymptote. Okay. So in this case, we have x squared minus 9 divided by 3x cubed. So what is going to go here? We need 3x. That gives me 3x cubed minus 27x. We're going to change the signs, and this goes away, leaves me with 27x. This is my remainder. We don't worry about the remainder. So this is my slant occurs at y equals 3x. And that is my slant asymptote. Okay, question. Okay. So now let's look at when we want to graph rational functions, right? We've looked at x and y intercepts over the course of this chapter. We've now looked at asymptotes. We've looked at symmetry, right? Is it symmetric with respect to the x or the origin? And now all we have to do is we can plot some points and we can get a good representation of what that graph would look like without actually building long, busy tables with lots of calculation. Okay. So if I want to graph this problem here, let's go ahead and calculate our x and y intercepts, our asymptotes, and then see if there's any symmetry with it. And we may need to plot a couple of points, but we won't have to plot every number on this x-axis to get a good idea of what that graph looks like. Okay, so let's start with our x-intercept. And so remember our x-intercept, we're going to just take our numerator and let's factor that out. And we'll factor that out, and let me do one little change. This, I'm going to make a 6. That is a typo there. Okay. And so when we look at this, we have our x squared minus x minus 6. Set that equal to 0. So we can factor that as x minus 3, x plus 2. Therefore, x is either 3 or x is negative 2. Therefore, that makes our actual x and y, or our x intercepts 3, 0 and negative 2, 0. Okay, so we could actually come over here. At 3, 0, we have a point, and at negative 2, 0, we have another point. Okay. Now let's look at our y-intercepts. I'm going to put that up here. That is our y-intercept. Remember, that occurs when we set our x value equal to 0 in our function. And so that equals 0 squared minus 0 minus 6 over 0 squared minus 5 times 0 minus 6. So negative 6 over negative 6 equals 1. So that value is at 0, 1. So we can come plot, here is my y-intercept. And I'm trying to just use lots of different colors to help y'all see where the work leads to the graph. Okay. Our vertical asymptote. Our vertical asymptote is where our denominator is equal to 0. So that is x squared minus 5x minus 6. Let's set that equal to 0 to determine that. So we have x minus 6, x plus 1 is how that factors. Therefore, either x equals 6 or at x equal -1, we have those vertical asymptotes. So let's come over here, x equal -1. We'll put in our first vertical asymptote and x equal to 6. So actually it's fine. Let's just change this portion. So instead of that being, so each of these lines were geared to be 2, but let's just call this an 8 and this a -4. Okay. Green. So our other asymptote is at +6. So 1, 2, 3, 4, 5, 6. Okay. So now we've put on our asymptotes. Now let's look for a horizontal asymptote. So a horizontal asymptote, remember that is, we have x squared over x squared. They're equal. Therefore, our horizontal asymptote is when y equals 1. So we'll put in that asymptote in here. And now let's look for symmetry. So for symmetry, that is, if we plug in f of -x, that equals x squared plus x minus 6, right? So I've just plugged in a -x for all of these, divided by, that's still going to be x squared, but this is plus 5x minus 6. That is not equal to my original, and it is not equal to negative of my entire function. Therefore, there is no symmetry, okay, with respect to either origin. So the only other thing is we don't really know what the shape looks like on this section over here. We could plot a few points. Let's go with this color. So if we make a table just to get a couple of extra points here, we can look at, here's -1, 2, here's -3. So we can see how does the behavior of this behave. So if I plug -3 into my original equation, I get out a positive 1/3. So that is going to be this point somewhere about right here. If I want to do 1 point on here, if this is 3, if I want to look at x equal to 4, I can plug that in and I get a -0.6. So if that's 4, here's half, a little more than half would be right here. So I could get that, and let me just make these also +5 so that they're not 2. So this is 5 and -5. And then the last one, we can look outside on the other side of that asymptote. So we plug in 7 and we'll get 4.5. So if I come over here to 7, I'm going to be up here at 1, 2, 3, 4. We'll say somewhere up here, like around 4.5. And so these graphs we can see would behave something like this because it follows along those asymptotes, right? This one is way up here. It's going to come down like this, okay? And remember, we can cross our horizontal asymptote for this middle piece, but you notice the two outer pieces, that asymptote was there as a guide, okay? So if you were to put this equation into your graphing calculator, you would get something that looks a little bit like what we have here on the right. Okay, question. Okay, a couple of more graphs and then we'll take a break. So this next one, we're looking at our, I won't change the colors as much this time, just I wanted to point out all the different things in the last one. But so if we're looking at our x-intercept here, that's going to be our 2x squared is equal to 0. And so therefore x equals 0. So we're going to have an x-intercept at 0, 0. Okay. We're looking at our y-intercept. That is where our x is equal to 0. So that's going to be 0 over -4. And so that is also going to be 0. And we have a y-intercept at 0, 0 as well. Okay. Our vertical asymptotes, remember that's where our denominator is equal to 0. So x squared minus 4 equals 0. That gives me x squared equals 4. Take the square root of both sides, and I get that x is equal to plus or minus 2. So I would come over here. Here's -2. Put in that asymptote. +2. I'm going to put in that asymptote. Okay. Let's look at horizontal asymptotes. That is, we have this 2x squared over x squared. You could see that they are the same. So we have an asymptote at y equal to 2. So we put that onto our graph. Then we're going to look at symmetry. So we have f of -x, and that is 2x squared over x squared minus 4, which is equal to my original equation. So I have symmetry to the y-axis. Okay, so that means if I fold it on the y-axis, I am going to get the same thing on the left as I have on the right. So let's build us a little table to help us fill in any of the gaps. And we want to pick one on each side of the asymptotes and maybe 2 in the middle, one on each side of the axis. Okay. So let's look at -3, -1, 1, and 3. So we plug in -3, we get out 3.6. We plug in -1, we get -2/3. Plug in +1, we get -2/3. That's that symmetry. And we plug in +3 and we get 3.6 as well. Okay. So let's go ahead and plot some of those points. We have -3, and then we are up here at 1, 2, 3, almost 4. And then -1, and we're down at -2/3. And +1 down at 2/3, -2/3. And then at +3, we're up here at 3.6. So this tells us that we're going to have this like this. Okay. And this one, because of that symmetry, we end up with a upside down parabola. Okay. Question. Okay, so this next example, we're actually going to have a slant asymptote because if you notice, we have 1 degree higher in our numerator than we do in our denominator. So let's go ahead and calculate our x-intercept. So that is 2x squared minus 8x plus 8 equal to 0. If we divide everything by 2, this is really the same as x squared minus 4x plus 8 equal to 0. So now we can factor that as x minus 2 squared equal to 0. So x is equal to 2. So we have a y-intercept at 2, 0. I mean, an x-intercept at 2, 0. We come over here, 1, 2, 0. We have a point. Our y-intercept is where we let our x is equal to 0. And so that is going to be is 8 over negative 3. And so that gives us the point 0, negative 8/3. So we come over here, 0, 8/3 is not quite a negative 3. Notice that these are in threes. So this line right here is 3, so we're not quite at that negative 3. Okay. So for our vertical asymptote, we have x minus 3 is equal to 0, so x equal to 3. So again, this was a 15, so I need to actually move this over here to where it is at 2, not the second line. So at x equal to 3, we have this vertical asymptote. And the horizontal asymptote does not exist, right? Because we already determined that we have a slant here because our numerator is exactly 1 degree larger than our denominator. So to calculate our slant asymptote, remember that is we have to divide the numerator and the denominator. So this is x minus 3 divided by 2x squared minus 8x plus 8. That's going to give me 2x. So that's 2x squared minus 6x. Let's change our signs. Those cancel. This leaves me with negative 2x plus 8. So this will be negative 2. That gives me negative 2x minus 6. Change our signs. Actually, that should have been initially a positive because you have negative 2 times negative 3. So those cancel. This sign becomes a negative, and we're left with 2 here. The remainder doesn't really matter, remember? So our slant asymptote occurs at 2x minus 2. So when you do that, we have to plug that in here, right? So if we go to our where we cross our axis, we can create our slant asymptote. Here we have this negative, so let's plot negative 2. So I'm going to put that in a different shade, right? So I come to negative 2. That is 1, 2. So we put a dot here and we just do rise over run. So we rise 2, run 1, rise 2, run 1, right? And so we end up with something that looks about like this for our asymptote, right? For the slant asymptote. So now you see we have this slant where we have our graph is actually going to fit right in here and right in here. And so we're going to calculate a few points to help us determine a little bit more refinements on that. Okay, so we have X and Y, and so we can do -3, -1. I'm going to do 1, 4, and 5 just because we have a couple of points in this bottom piece, but not in the top piece. So if I plug -3 into my original equation, I get -8.3. If I plug -1, I get -4.5. If I put 1, I get a -1, 4, I get 8, and 5, I get a 9. So let's plot those points. So we have -3 gives me -8.3, so that's down about right here. If I plug in -1, that is -4.5 or so, so it's somewhere around right here. If I plug in +1, I get -1, so I'm like somewhere around like right here. You see, we're kind of building this, and then it'll come back down here like this, coming in line with this asymptote. When I plug in 4, that's just this side to the right side of my one asymptote. I'm up at 8, so that's 3, 6, here's 9, so 8 would be somewhere around right here. And 5 would be up at 9, so it's somewhere like about right here. And so this one is going to look something like this. And it doesn't have to be exact when you're graphing these. And on your exam, I'm not gonna give you a slant one to graph. I may ask you what a slant asymptote is, but I'm not gonna ask you to graph the slant. Because they can be a little tedious, and without graph paper and that sort of stuff, it makes it a little bit more difficult and challenging. But you will see them in your homework problems that you get to practice in ALEC. Okay, question. Okay, so for the last thing here, we're just going to look at this graph, use transformations to do this. So first of all, what is the parent graph? So here our parent graph is really just 1 over x, okay? And when we look at this, we can start looking at the shifts. So I will say, if you look at this right here, that tells us that we shift right 3 units, right? So that means then that we have this new vertical asymptote at x equal to 3, okay? And what else do we have? We also have this part right here, right? That tells me that I'm going to shift down 1 unit. Therefore, I have this new, let me move this down. I have a new horizontal asymptote at y equal to -1, okay? So come in here, x equal to 3. I have this this vertical asymptote at y equal -1. I have this asymptote, and now it's really just graphing that parent function that we learned back in week 1, where we have a graph that looks like this. But that transformation told us exactly where to shift our asymptotes to help guide us for that graph. Okay, question. All right, so we have one more section of new material before we get to the exam review. But before we start this one, it is 8:06. So let's come back at 8:15. So take a 9-minute break. We'll come back at 8:15. So stretch your legs, get a drink of water, whatever. And then we'll come back at 8:15 and we will continue on. Okay. All right, it is 8:15, so let's go ahead and keep moving forward with this section. So the final section that we have here is going to be looking at inequalities. So sometimes we'll have a couple of different polynomials or a polynomial that has multiple pieces, and we want to determine on what intervals it is positive and which intervals it is negative. So for example, this problem that we have right here, this is actually x squared. We're just going to distribute this. This gives us x squared minus 2x minus 15 is equal to 0. Okay. Because we've moved the 15 to the other side. So we really want to just factor this out. This factors to x minus 5, x plus 5. Okay. So x equals 5 or x equals negative 3. And so why do we do this, right? So we can build kind of a little timeline here. And so if we put the smallest one here, so negative 3 and 5. So these are the two places where we would end up with 0. Okay. So we want to have a test value. We want to test a value on every side of the value that we have here. Okay. So if you think of these as like boundaries, kind of, right? So I want to test something in this section, and this section. So what are those values? So we can't test the value that is on the line or what makes it a 0. I always say we should always use 0 when it's available. If it's not on one of those lines, we're always using 0 because it's the easiest to calculate. And I usually just go one value off of the line. So if that's 5, one more is 6. If this is negative 3, one more is negative 4. Okay. And we want to test our values here. We have the x minus 5 and we had x plus 3. Okay. So if I plug this 4 into each of these, right, I get negative 4 minus 5. That's going to give me a negative value, right? It'll give me negative 9. If I plug negative 4 into this one, I get negative 4 plus 3. That is also a negative value. Okay. Now, think about that. If I do negative times negative, then that's going to give me a positive value down here. Okay. So basically, think about that. If I had x equal to negative 4, that would be negative 9 times negative 1, and that is positive. Okay. Similarly, if I plug the 0 in here, I'm going to get negative 5. If I plug the 0 in here, I get a positive. So a negative times a positive is a negative. And if I plug 6 in, I'm going to get positive, and the 6 in over here, I get positive. Positive times positive is positive. So this problem was saying, where am I less than? So where am I negative? So here is where I am negative, and it is on that interval from negative 3 to positive 5. I have brackets because I don't have a restriction. I don't have, like, if this had been in a denominator, then I would have parentheses because the zeros would make me undefined. But here, there's nothing saying that I cannot have a 0 value. It's just asking on what interval is my graph negative. And so we can come over here and look. Here is negative 3. Here's positive 5 right here. And you can see that in this whole section from negative 3 to negative 5, our graph is negative. It's in the negative. I mean, from negative 3 to positive 5, our graph is y values are negative. Greater than that, our y values are positive. Okay? Question. We're going to have quite a bit of practice at this. Okay? So always build this little table. I promise you it makes it easier. So for this one, we can see that our values are x is 2 and negative 3 makes our values 0. So we have negative 3 and 2. So this is kind of our boundaries. We have x minus 2 squared, and we have x plus 3. Okay, so when we're looking at this, let's find ourselves negative 3. So let's test negative 4. Always testing 0 when available, and here we'll test the value of 3. So negative 4 minus 2 is negative 6. Negative 6 squared is always going to be positive. Negative 4 plus 3 is negative 1. So that's going to be negative. So positive times negative gives me negative. Okay. Plugging in the 0, I'm going to get positive. Anytime I square anything, I'm going to be positive. So that's going to be positive all the way across the board. 0 plus 3, that's positive. 3 plus 3, that is positive. So we have positive times positive is positive. Okay. So when we have this problem, we're looking at, so this one was, we want negative, but equality was okay, right? Because there was equality. So that's why we got to have those brackets. On this one, there's no equality here, so it can't be equal to that value. It can strictly be greater than, right? So to be strictly greater than, that means I have to have a hollow on these because I cannot equal. I have to be greater than, okay? So for my intervals here, because here that's where I equal 0 at these, but I want to be greater than 0, okay? So that's going to occur here from negative 3 to 2, and then again from 2 to infinity, and I have parentheses on all of those again because there's no equality in that symbol, okay? Now, I will write over here, if it had been greater than or equal to, then we would have had negative 3 all the way to infinity. Okay? But it didn't have equality, so we don't have that. Okay? Question. Okay? And so we can look at this example here. We had negative 3 to positive 2. You could see the whole graph is above here. And then again from 2 all the way up to infinity. And the reason that it doesn't include those values is because it is equal to 0 at those points. Okay? Question. Okay, for this next one, we have this, we do see that there's some equality in this graph, right? So for this one, we have that is 2x minus 5. It's going to be squared. So x equals 5 halves. But the thing is, when you have 2x minus 5 squared, that's always positive, right? Because anytime you square something, it's positive. So you're never less than 0. You're never less than or equal. You could be equal, but you'll never be less than 0. Okay? You can only be equal to 0. And that occurs at x equal 5/2. Okay? So this one would only have a solution of 5/2, which is right here, where it meets the inequality. And you see there's nothing below the x-axis because there's no value that makes that less than. Okay? Question. You can see these are the same equation, but we're just changing what we see here in the equality. So when we take that equality away from here, again, we're at the 2x minus 5 squared. And where does that equal less than 0? That never happens, right? So it's never negative. Therefore, we would say it's a empty set. You would do an empty braces, or you could do this 0 with the line through it, or you could write no solution. Okay. And so basically what that's saying is there's never a point where all of that stuff on the left-hand side is less than 0. Okay. And then if we had greater than, right? So again, that's the 2x minus 5 squared. Where's that greater than or equal to 0? Well, it's always positive or 0. So my solution would be negative infinity to infinity. So every value would be a solution if the equality was greater than or equal. Okay, question. Okay, let's look at this next example then. So in this problem, we have three things that could make it a 0. So x equal +1, -3, or +4. If any of those three values take place, then we would have a 0. Okay. But we also have to pay particular attention that if x equals 4, it cannot equal 4, right? Because then we have something that is undefined. So when we build out our table here, again, remember we want to list it. Think of this as if it was a number line. So we want our smallest values of x here. So -3 is the smallest, and then 1, and then 4. I'm going to go ahead and put a hollow dot right here because this is where my denominator is undefined. So I know even if this becomes part of a solution, I cannot have a bracket on this. I have to have a parentheses on the 4 because the 4 cannot be included because of that asymptote. Okay. So let's go ahead and put that one here. These values. So our test values, we have x minus 1, we have x plus 3, and we have x minus 4. These are our test values. Okay. Put this one down just a little. All right. So now let's look at it. Let's pick some values. So if this is 1 or -3, so we can choose a test value of -4. Between +1 and -3, that's where we can check our 0. And here we could test a 2. And on this side, we could test a 5. So we want to test on all sides of those values, okay? So for our first one, when we plug -4 in here, we get a -5, so that's negative. -4 into here, we get -1, that's negative. -4 into this one, we get negative. So when we do a negative times a negative times a negative, that is negative, okay? When we plug in the 0, we get negative, we get a positive, we get a negative. So here we have negative times negative is a positive. Now when we plug in the 2, we get positive, positive, negative. So this will be a negative because positive times negative is negative. When we plug the 5 in, we get positive, positive, positive. So all of those will be positive. Now, what did our solution ask us for? Our solution asked us for, we want to be less than or equal to 0. So equality is okay, except at 4, right? We can't be equal to 4, okay? And we want to be less than, so this is my negatives, okay? So my negative is from negative infinity to -3, but I can include -3, so we'll put a bracket, okay? And then I can come over here and I can say, and I'm going to go from +1. I can include +1. It's not in the denominator, up to 4, but I have to put a parenthesis on the 4 because I cannot include the value of 4. I can only include everything up to 4. Okay? Question. So that would be that inequality solution in interval. Okay? Any question? All right. Here is another problem. So in this case, now we don't have that 0 on the other side, right? So we have to solve it till we get the 0 to be able to do the technique that I have taught you all. So in this case, we would -3 from both sides. So we end up with x minus 5 over x minus 7 minus 3 is less than 0. So all I did was -3 from both sides. Now I need to get a common denominator. So a common denominator would be x minus 5 over x minus 7 minus 3 times x minus 7 over x minus 7, right? Because x minus 7 over x minus 7 is just 1, and we can do that. So in doing that, that is less than 0. So this is -3x plus 21. So that gives me -2x when I combine those. So -3 plus 1x gives me -2x minus this was -21. Let me see. Yeah, -21, not -2x, sorry. That gives me -3x, yeah, 2x. So this gives me 21, -21, or +21, because we have -3 times -7 is 21 minus 5. So that's going to give me +16 over x minus 7, and that is less than 0. Okay? So I can do one more step, and I have -2, factor that out, and I have x minus 8 over x minus 7 is less than 0. So x equals 8 or 7. Okay. So now we can build our, so it's 7 and 8. Okay. And so we have, I'm going to go back to the negative 2x. Let me move it out. Negative 2x plus 16, right? For our numerator, and x minus 7 for our denominator. I'll just scoot that over a little bit. Okay. And so our values that we have to choose, we can choose 6 over here. Actually, let's choose 0 because 0 is always the easiest. Here we could do 7.5, and here we can choose 9. Because I can't choose 7, I can't choose 8, so I have to choose something in between. Okay, so when I plug 0 in over here, I get positive and negative, so that's going to give me a negative value. When I plug 7.5, I end up with positive and positive, so when multiplied together, it'll be positive. When I plug the 9 in, I get negative and positive, which will be negative. Okay, so this problem was asking us, where are we less than, right? So where are we negative without equality? So that means these values will have hollow or parentheses if they're included because the equality doesn't exist. And I'm gonna do that and put negative, right? So no equality. So that's where you have hollow or parentheses. Okay. So in this case, it's saying for negative. So we're negative from negative infinity up to 7 with the parentheses. And then we're also negative from 8 up to positive infinity. Again, parentheses on that as well, because the equality doesn't exist in this problem. Okay. Question. All right. One last problem. So you can see this one's a little more complex, right? We have these fractions on both sides of the equality sign, but we need to move one over to the other side so that we can get it equal to 0. Because to be able to implement the technique that I've showed you, we have to have our equality set to 0. Okay. So this gives me 1 over x plus 6. I'm going to just minus the 3 over x minus 2 from both sides, and that is greater than or equal to 0. Okay. Now let's get a common denominator. So I'm going to multiply x minus 2 over x plus 6. And that is because you're kind of just cross multiplying to get that common denominator, minus 3 over 3 times x plus 6 over x minus 2. All of that is still greater than or equal to 0. And that is because we have this x minus 2 here, and I'm going to scoot this x plus 6 over here, right? So we're just getting common denominator. So this gives me, combining everything under one roof, we have x minus 2 minus 3x minus 18 divided by our common denominator of x minus 2, x plus 6. Okay, and all of that greater than or equal to 0. So we get common terms up in the numerator. So we have a negative 2x minus 20 divided by x minus 2x plus 6. greater than or equal to 0. Now we can factor this negative out of the numerator. So we have negative, and then we have 2x plus 20. And I'm doing this because I want to show you guys just a reminder of some of the rules of inequalities. So now I want to multiply both sides by -1 to get rid of this -1 here, okay? And so I multiply by -1. When you remember, when dealing with inequalities, if you multiply or divide by a negative, you must flip the sign. Not if you add or subtract, but if you multiply or divide by a negative, you must flip the sign, okay? So in this case, we're multiplying by a negative. So now we have 2x plus 20 over x minus 2, x plus 6. We have to flip our sign. So instead of greater than or equal, now it's less than or equal to 0. Okay, so we flipped the sign because we multiplied or divided by a negative. Okay, so in this case, my x can be -10, 2, or -6. So let's build. We have -10, -6, and 2. Okay, I'm going to move this down just a little bit. Okay, so our things are, we have 2x plus 20, we have x minus 2, and x plus 6. Okay, so what values do we want to use? This could be -11, this could be -7, this could be 0, and this could be 3. Okay, so when we plug in -11, we get negative, negative, negative. So 3 negatives makes a negative. When we plug in -7, we get a positive, negative, negative. So that's going to give us positive. When we plug in a 0, we get positive, positive, negative. Multiply those together, it'll give us a negative. And when we plug in the 3, we get positive, positive, positive. So that'll be a positive. So one thing I do want to point out is we got to look at our denominator. This makes our denominator undefined. And this one also would make our denominator undefined. So these are things that make our denominator undefined. So we have to have those. We cannot have equality with the -6 or the 2. We can only use parentheses. Okay. So that, excuse me, gives us, we're looking for the value where it is greater than. So we're looking at a value of positive. Okay, so we're positive here and here. So actually, if we look back at our overall problem, I don't know, like we're not looking at that one, we're looking at this one because it's after the sign, we want to look at negative, right? And so we're negative here and here. I want to give this a different color. Negative. Here and here. And so how does that work? We have negative infinity to negative 10, but we can have equality with the negative 10. And then again, we're over here from negative 6 to positive 2, but we cannot have equality with either the negative 6 or the 2 because of that asymptote from our denominator. Okay? Question. All right, so that is the conclusion of chapter 2. At this point, we will transition to our exam 2 review. The exam 2 review, or the exam 2 will take place 2 weeks from tonight. So there's no class next week, no exam next week because it's spring break. Okay. So you guys will have your exam on the Monday following spring break. That is the 18th. So we won't have a lecture that day, but you will have to log in, do the exam, and so forth. So the exam is 15 questions out of chapter 2. And you will have 90 minutes, just like last class, just like last exam. You will need to make sure that you show all of your work, and you must submit your work in Canvas within 15 minutes of completing the exam. Most of you did a really good job making sure you did the naming convention correctly. The thing that is most important is that you start your file with your last name, because what happens is I download all of the exams and then I grade them, and then I have to put them back up in with your name. And so that's why it's important that you associate your last name with your file. The other thing is you must put all of your photos in one file, and that one file then again starts with your last name. I did not take off points this time, but I noted, and you should go look at your exam for those of you who maybe didn't do it 100% correct. Let exam 1 serve as the warning, like how to do it correctly. You've had plenty of time. You can come back and ask for further guidance if you need assistance with that. But on exam 2 and moving forward, if the naming convention isn't done with your last name first and all of your documents are not in one file, there will be a 5-point deduction from your exam. So you want to make sure that you are doing it correctly. If you need to practice more, let me know. I could put more practice in attempts in on that one homework assignment that we were given back in week 1. Okay. All right. Any questions before we start the review? Okay. So this first page here really just points you into the problems that you might want to focus in on to study. As you probably noticed from the first exam, I really do not put any surprises on there. I give you everything that you need to be successful. You just have to take that information and practice and study with it to become proficient with the material. Okay. All right. So the first problem is you'll be asked to basically you'll be given an equation, be asked to put it in vertex form. What are the what is the vertex? What are the X and Y intercepts? We've kind of gone over all of this where what I will do for this is when you look at this, you'll want to use completing the squares. So I'll put that here as a pointer, completing the squares. You'll do that here. When you do that, you will end up with 3x minus 3 squared minus 1, right? So then from there, you know that the vertex is your h comma k. So our vertex here is 3, negative 1. Our x-intercepts, that is where we're going to let our x equal to 0. Our not x equal to 0, where we set our whole equation equal to 0 and solve out, and we get 9 plus the square root of 3 over 3 comma 0, and 9 minus the square root of 3 over 3 comma 0. Remember, and you probably noticed some of you missed points on the first exam, an intercept must have a coordinate point, not just x equals something or y equal to something, okay? And our y-intercept here is 0, 26. And so we would be, we have this 0, 26 is something like way up here. And because we have symmetry, we would have these points here. To something similar like this. For that graph. So really what I'm giving you here is a solution manual to go along with these so that you can take the practice one that I've put into Canvas, into our classroom in the modules, print it off, write it on your paper, whatever, and then come back and reference our video from lecture and see if you are able to solve those correctly. In addition to these, you can work other ones from this slide in the textbook. All the odd problems have solutions in the back of the book in the appendix, okay? All right, so another problem is you're going to be asked to, remember when we were going over it in class, I told you would have a problem where you needed to determine the vertex using the vertex formula. And so remember, you've got to remember this, the formula is not provided to you, but that's the negative b over 2a. And then you plug that into your function, whatever you solve out for that, and that will give you your coordinates. And in this case, it is 3, negative 14. Okay, question. You'll need to do the end behavior. So remember we had if this is positive or negative, and if this is odd or even, we have the 4 different cases there, right? So in this case, as x approaches negative infinity, my whole function approaches negative infinity. And that is because if we look at our end behavior, we know that we're decreasing to the left and we're decreasing to the right. So in both cases, we're going to be heading to negative infinity. And that's all based on the end behavior of that negative 3x to the 4. So we're negative and positive, or negative and the even exponent. So we're dropping both to the left and the right. Okay. Any questions on end behavior? This next one, you're finding the zeros and stating what their multiplicities are. So in this case, you'll want to factor this equation. This one looks like you could take a negative 2x out of it to start with. What are you left with on the inside? You can factor that out and you'll get that your zeros in this case are 0, 5, and negative 3/5. They all have a multiplicity of 1. Okay. Any questions on finding zeros and multiplicity? So you'll have another graph here where you're given an equation, you're asked to identify the end behavior. So this, we're positive and even. So our end behavior is going to be up in both directions. And our y-intercept is going to occur at 0, 0. So when we let x equal 0, our y also equals 0 in this case. And then we have real zeros at 0, -2, and 3. So in this case, we would have, here's -2, that's a 0. We had a 0 at 0 and a 0 here at 3. We're in the up direction, right, for both of those. And so this is, we're going to, when we look at this, when we look at multiplicities and such, we have 0 with multiplicity of 2. Therefore, we're going to just touch the axis and come back down. Okay, and so that is, we have 4 as our exponent, but we only had 3 zeros, and that's because this one had multiplicity of 2. Okay? Question. Okay? Long division. So there will be a problem. It'll say you must do long division for this. So to set this up, it would be 2x plus 8 divided by, this has to be in descending order, but you see we're missing some. So this is 6x to the 4 plus 0x cubed minus 92x squared plus 0x minus 64. Okay, very important. Don't forget to put in all those placeholders in there. When you do all of that, you end up with 3x cubed minus 12x squared plus 2x minus 8. And you'll have a remainder of 0 in this case. Okay? Any questions on long division? So remember, when you get whatever value you are here, you change all of the signs, add them together, and move and bring down the next value. Okay? Synthetic division. So if I'm saying x, this whole equation divided by x plus 2, that's saying that x equals -2 is a 0, right? So x plus 2 is a factor, x minus 2 is a 0. So I'm putting the -2, I put the 0 over in the box. Again, this one is out of order, so let's put it in order. So this would be -3. I have no x cubes. I have -7x squared, -4x, and a +2. Do all of that. And so in this case, I end up with -3x cubed plus 6x squared minus 19x plus 34 minus, my remainder is 66. So I put it over x plus 2. I put it over my factor there. Okay, question.
Yeah, I have a question.
Sure.
So for long division, let's say we go through everything and we get the, we did it all, right? And we have our answer. Would a good way of checking if the answer is right doing the problem in synthetic division and comparing that? Because I know synthetic division is easier than long. So would we get the same result? Is that a good way of checking that or no?
You would, except on the exam, I'm going to give you one like this, and this kind of problem you can't do with synthetic division.
Oh, okay.
Well,
Okay.
actually, this one you could. You could because you could do 2x plus 8. What makes that equal to 0? A minus 8. So that's 2x equals negative 8. So x equals, right? You could do it here for this one, but on the exam, you might get something like x squared plus 1 for that, and you can't do that. Remember when we did that module? You could if it's linear, but if it isn't linear, you have to use long division.
Okay. Okay. Thank you.
I will say though, if you make one small little mistake, like you said, this was plus and it should have been a minus, I give you most of the points on the problem.
Okay. Thank you.
Okay. Now let's look at the remainder theorem. So in this case, we want to know, is C equal to 7? Is that a 0 for this, right? So in this case, you want to use synthetic division. Okay. Do synthetic division, and if the remainder equals 0, then it's a 0. Okay. In this case, C equals 7 is not a 0. Because you go all the way down, you get synthetic division, and let's say this is a 5, right? Your last position. If that is not a 0, then it is not a 0. So if your remainder is not equal to 0, then whatever value you did in the synthetic division, whatever value that is not a 0. Okay? Question. All right, so in this one, we're listing all of the possible rational zeros of x, right? So in this case, we're looking at, when we want to look at the possible zeros, that is, we're looking at our factors of 24 divided by our factors of 3, right? So all of those that pan out, remember it's all the plus and minus divided by the plus and minuses, right? In this case, the actual zeros, if you're wanting to practice further with this problem, the zeros of this problem are -3, -1, 2/3, and 4. Okay. Question. So for this one, we're writing the lowest degree polynomial, given that -4 is a 0, multiplicity 0, and 1 is a 0 with multiplicity of 1, and that f of 0 is equal to 16, right? So we did a problem like this earlier today. So you guys will have some opportunity to practice that. You guys can practice this one as well. And you should get -4x squared minus 12x plus 16. Okay, so just work through that and see if you get to that. If you're working through it and you get hung up on something, feel free to shoot me an email. I am not going anywhere for spring break. I'll be around. I may not be checking my email every day, but if you send me an email, I will say I will get back to you within 2 days since it'll be spring break. And we don't have to, but I will, because I want to make sure that you guys are prepared for the exam on the Monday that we come back. Okay. So over spring break, even though it's spring break, I will check my email at least every other day. So please feel free to send me any questions you might have as you're studying, if you choose to study over spring break. Or this week leading up to spring break. So you really have 2 weeks to prepare for the exam. Okay, so for this one, this is where we're trying to determine the number of positive and negative zeros. So remember, we're doing our sign changes. So we change signs here and we change signs here. So we had 2 sign changes. So we're either 2 or 0. Remember, because we have to keep decrementing that by 2 until we get to 1 or 0. We can also remember where we do our f of negative x. So that's changing the signs of all of our odd exponents. So that becomes negative 3x to the 5 plus 4x to the 4 plus 7x cubed minus 2x squared minus 5x plus 2. And so then when we look at this one, we have a sign change, a sign change, and a sign change. So we have either 3 or 1 sign changes. Okay. Another example of this would be if I had come up with 6 sign changes, right? So I would say that 6, 4, 2, or 0. All right. If I had come up with 7 sign changes, then that would be 7, 5, 3, or 1. Okay, so you have to do that. You can't just say 3. If you don't go 3 or 1, then you'll lose a little bit of points because you missed some of the potential negative. Okay, any question? So this one, if I want to know the domain of the function, I can do that. I know that x cannot equal 2 because that makes me undefined. And so then the domain is what values can x take on. It can be anything from negative infinity to 2, but it cannot equal 2. So then it can also be from positive 2 to positive infinity. And so this is my domain in interval form. Okay. Question. Okay. So this next problem, if you were to graph of this problem, so we can look here, we can see that our x is equal, our exponent is equal in the numerator and the denominator. So our y is equal to 2 over 1. So that is, we have a horizontal asymptote at y equal to 2. Our vertical asymptote occurs when x equals -3 because that's what makes our denominator undefined. And if I have a horizontal asymptote, I will not have a slant asymptote. And so then if I needed to graph these, I have my vertical asymptote here at -3, my horizontal asymptote at +2, and then we can do some other points to help us see where that graph gets plotted. Okay, we can calculate our x and y intercepts as things to help us if we need. We kind of got a lot of that practice today and last class period on those. Okay. Questions? For this next one, if you're asked to solve the inequality, again, make sure you remember if you multiply or divide by a negative, you have to flip that sign. So this one would be -8/5, 8/5 when you solve this out. So add 64 to both sides, divide both sides by 25, take the square root of both sides, reduce that, and that is what you should get here. Okay. What else? One more problem, I think. Yep. So the interval, like what we just finished doing here, this right here, remember that's going to give me a vertical asymptote at x equal -6. So when you're building out your thing at -6, remember that's going to be hollow. And our interval ends up being -6 to -2, where -2 can be included. And then again, from 4 to infinity. And remember, infinity and negative infinity always get parentheses because we can't actually get to an exact location, right? Because just as we think we get to it, there's something else even further out there. So we can't ever actually attain infinity or negative infinity. And so that's why it always gets the parens and not a bracket. Okay? Question. All right. So that is all of the material that I have for you all this evening. That gets us through chapter 2. Once we come back from spring break and take this exam, we'll be about halfway done with the course material. Do you guys have any questions, comments, concerns, anything of that nature? All right, if you guys don't have any questions, you are free to go. Don't forget, if you have questions between now and the 18th when we have the exam, please just send me an email and I will get back to you as soon as possible. Other than that, no class next week, no class the week after that, no actual lecture, we'll have exam. And you guys have a great, safe spring break, and I will see you in a few weeks.
I'm sorry, I just thought of a question.
Go ahead.
So is the homework that's usually assigned for 1 week, is it because of spring break, is it 2 weeks
Yeah.
now?
Yes.
Okay, so now we have 2 weeks for this assignment, this homework assignment this week's. Okay, thank you.
You're welcome.
Good night.
Good night.
Good night.
Good night.